Hello everyone, welcome back to learn the actually loaded member. In this lesson, we will learn the global buckling of actually loaded compression members and their influencing factors. For an actually loaded compression member, two types of filler modes would occur. Firstly, for a short column with its component plant elements being provided from local buckling, the filler of the column occurs by strength filler. Secondly, for a long column, the filler of the column occurs by global buckling. Since we have mentioned the words stirability and buckling, here let's figure out some basic concepts. What is the stirability of a structure, and what is the global buckling of actually loaded compression members? Well, the so-called stirability is the ability of members to maintain their equilibrium state under a certain deformation due to an applied load. When a long actually loaded column undertakes a certain degree of a compression force, a large deformation may occur on the member, breaking its stability and resulting in a loss of bear capacity. Such a phenomenon is called the global buckling of actually loaded compression member. Since the strength of a structural steel is high and the planks used to make up of the steel components are thin and weaned, the steel structure members are easy to lose its stability. Therefore, global buckling is an important issue in the design of a steel structure. For an actually loaded compression member, we can first discuss the global buckling of an ideal compression member. Then, based on the results obtained from the ideal compression member, we can derive the design methods for a real actually loaded compression member in practical engineering. A member can be defined as an ideal compression member if the following conditions can be satisfied. Firstly, the compression member is strictly straight. Secondly, the cross-section of members is uniform along the member's axis. Third, no imperfections exist on the member. For an ideal axial compression member, three different buckling modes may occur. Well, the first buckling mode is flexural buckling. In this mode, the member fails by excessive deflection in the plane of the weaker principal axis. Flexural buckling is a common buckling mode for most of doubly symmetric section columns. The buckling filler that occurred in the plane of a symmetric axis of a singly symmetric section column also belongs to this scope. The second buckling mode is torsional buckling. In this buckling mode, each cross-section of the column will twist about the shear center in the longitudinal axis of the member. This buckling mode is a possible buckling mode for a few doubly symmetric section columns. For example, a short cross-shaped section column would fail in such a buckling mode. Well, the third buckling mode is flexural torsional buckling. In this buckling mode, a combination of flexure and twisting would occur in the column simultaneously. The buckling filler in the unsymmetrical axis plane of a singly symmetric section column is an example of this type of filler. Since the flexural buckling is the simplest and most common filler mode of an axial compression member, here we mainly discuss the flexural buckling of the axial compression member. In the course of mechanics of materials, we have studied the elastic buckling critical load of an ideal slender compression member. Euler derived the critical load of an ideal slender column with both ends hinged, as shown in equation 4-3 and 4-4. However, the Euler formula is not accurate for the column with an elastoplastic state. Thus, the tangent modulus 0 was used to obtain the corresponding flexural buckling critical load and critical stress. See equation 4-5. Well, in a real column, inevitable imperfections may exist on the column. These imperfections include mechanical imperfection and geometric imperfection, where the former one mainly refers to residual stress, whereas the later one includes the initial crookedness and the accidental eccentricity of a load. These imperfections have a strong influence on the buckling behavior of the column. Thus, we need to study their influence. First, let's look at the impact of a residual stress on the behavior of the compression member. Figure 5 shows the residual stress distributed on the cross-section of the I-section column. It can be found that the existence of a residual stress will result in parts of the cross-sections of the column stamping into the plastic state before global buckling occurring. This will reduce the flexural stiffness of the member along both two principal axes and thus reduce the overall stability capacity of the member. Second, the influence of the initial crookedness of members. Real compression member generally has small flexural deformations before loading. According to Figure 7, we can get the following conclusions. Firstly, the measured results show that the initial crookedness of the member is between 1 in 2000 to 1 in 500 of the column length. Secondly, the deflection of the column increases with the increase of the compression load. Third, the deflection of the column increases with the increase of the initial crookedness. Fourth, the stability bear capacity of the actually loaded compression member having initial crookedness is always smaller than the older critical force. Third, the influence of the eccentricity of a load. Due to the reasons such as constructional detail, cross-section, member processing, and insulation, the actual force at the end of the column can't strictly act at the centroid of the cross-sections. This deviation would result in an eccentricity of the load and reduce the stability capacity of the column. Since the effect of initial load eccentricity is similar to that of initial crookedness, we usually consider only one of them in the design. In the cold design of steel structures in China, only the influence of initial crookedness is considered, with the value of initial crookedness being as 1,000th of the member's span. Besides the factors mentioned above, the boundary condition of the column has the influence on the stability of the column as well. For a real compression member, the boundary conditions at the two ends of the column are not pinned like what Euler analyzed. For an actually loaded column with arbitrary supports, the critical load should be calculated according to equation 4-6, where L0 is the calculated length of the member, mu is the calculated length coefficient. Different end support conditions will result in different values of the calculated length coefficient. In summary, in this lesson, we learned the concept of global buckling of actually loaded compression members and their influencing factors. In the next lesson, we will learn the global buckling calculation methods of actually loaded compression members. See you next time.